Hello all. I guess we can start right now. Um, I am Arpa Prabhu Chaudhary. I am PMRF at IIT Bombay, Department of Chemistry. So I am Professor Anindya Datta's student, and as a PMRF, I am here to as a PMRF duty. I will be serving as a teaching assistant, so that I can conduct the live sessions for you to help you with the lecture materials, and also if you have any doubts, I will try to solve them, and we will solve some numerical problems that can help you to solve the assignment problem. That's my job is going to be, and we will sit twice, 2 hours a week, once a week, and the date and time is fixed as such that Tuesday 7 to 9 p.m. this p.m. and the link will be the same. So I hope as you have already started reading about the quantum chemistry and the week one, I think you have already studied. So today I will try to just go through the lecture slides what Professor Anila Datta has already taught you. And I'll, if you have any specific doubts regarding the week one material or as such in general regarding the course, you can ask me. If I know the answer, I will tell you who the answer, and if I don't know, I will go through the lectures or maybe some books, and will get back to you soon. So please don't be shy away to ask question. Uh, it's quantum chemistry. It seems like I know something, but eventually nobody understands quantum chemistry that way. So I hope it will be an interactive session. Um, Unfortunately, I do not have a video camera with my laptop, so I can't share my video here. But I will be sharing my screen so that we will discuss those parts. Uh, Before starting, do you have any specific queries till now from the week one or the overall lecture series as such? Any one of you? I guess no one is responding, so I will start with the discussion session. For record, I'm recording this session because I have to record. I have to record this whole session, and I have to upload this to a specific YouTube channel, and the link will be shared to you by the. I think one spreadsheet will be there or like a Excel file where the links will be there so that if any one of you is going to miss some classes, so that you can rewatch those videos. Uh, so you get some help out. So I'll be sharing my screen. I hope you can see my screen. So today will be the week one live session of quantum chemistry of atoms and molecules. And I have already introduced myself that I am Arpa Prabhu. I am a PMRF at Department of Chemistry at IIT Bombay. So I am in my fifth year of my research program, and soon, hopefully, soon we'll be finishing it off. So the objective, as I told you, to give you solution of weekly assignments and doubt clearing sessions. Uh, I will not be solving assignment which is not yet submitted by you. Suppose week one and week two, I guess the deadline is still there. So I'll not solve that. I'll try to solve similar problems so that it will help you to solve those assignments. So to begin with, I will just share these. As you already, I guess you have already seen these PDF files or slides shared by taught by Professor Datta, and these are professors from our department. And to many of you may have the query that what book should we follow, textbook. So mainly you can follow. Atkins 10th edition or Macquarie Simon's physical chemistry book, McCurry's quantum chemistry, Pillar's quantum chemistry, and obviously Ian Levine's physical chemistry edition. I will be solving the numerical problems. I have kept some numerical problems from Atkins actually. It is I guess the eighth chapter, the quantum chemistry, the introduction to quantum chemistry, and I will take some numerical problems from there and will solve them after discussing today's uh, session, not session, the lecture. So these are actually I am repeating myself that these are the notes already taught to you by Professor Datta. So I will not be elaborating each and every slide. Just go through them, and if you remember that you have any queries or doubts anywhere, just raising your hand. I won't be able to see you. Just unmute yourself and ask any question if you have any. Okay. I hope that's clear. So to start with, that what are we going to study? Ultimately, we want to know that what we are made of. What so it is already known that we are made of molecules. Molecules are made of atoms, and then again there are subatomic parts. But when it all started, that Thomson actually thought of an atom as a palm pudding model, where the it is a spherical cloud of positive charge, and then electrons or negatively charged electrons are there. But as you already know, that this is not a feasible condition. As you know that oppositely charged particles will attract each other and will annihilate very quickly, right? So this is not a feasible model, but the model to start with is this compounding model of function. And then comes Rutherford model of atom, which actually it gives us an idea that yes, there are role of orbits. How actually I think the professor has already discussed this part. I'll just quickly see that what are the key points we can discuss from here. That the alpha particle that are actually reflected back, uh, 1 in 20,000, that kind of probability, those are actually hitting the nucleus, right? Positively charged nucleus, it is reflecting back those positively charged alpha particles. Those which are many of them are actually transmitted because atoms are mostly empty, right? And most of them, some of them are getting scattered. Those are due to who some of them are getting scattered, right? From here, actually, Rutherford gives a model which is known as planetary models of atom, where he has told that at the central point there is the positively charged nucleus and electrons are going around. But there is a problem about that, that if negatively charged electrons are accelerating in motion, then they will radiate energy and eventually they will radiate energy continuously and they will eventually lose energy and fall onto the nucleus and it will get annihilated. And from mathematics, actually, it was known that the time taken to get annihilated will be 1 picosecond. So it's not a feasible model again, right? Like the computing model, we have some idea from the idea of atoms from here, but this is not a true model. So Niels Bohr actually comes into the saving grace, and from the experimental point of view, he told us actually that electrons. So see, at the center point, the nucleus is there. That statement is not changed, but about the specific orbits, means the stationary states are being introduced by Niels Bohr. He told that electrons will rotate in circular orbits of some specific energy, and those allowed orbits will follow this electrons angular momentum. That will be mvr will be equals to nh by 2 pi. And these states or these orbits will be called the stationary states, and they have a fixed energy. But these electrons can actually hop around these stationary states. They can go to a higher energy stationary state by absorbing some photon, or they can radiate some energy and go to the lower stationary states. And this energy will be equals to energy of going from hopping from one place to another is going to be equal to he, where h is the Planck constant. And from there on, what is a Planck constant? You know that the value is, I don't know if I can write it here. The value you know, right? The Planck constant, H is 6.626 into 10 to the power minus 26 joule second. It's not joule second inverse. So you have to be very careful about the units in physical chemistry. And we are going to solve some numerical problems where you will see that uh, you have to be very precise about the units in physical chemistry, mathematics specifically. Anyway, so from the black body radiation, actually, the Planck gives us his Planck distribution. Here it is. And the density of states can be given by this 8 pi AC by lambda to the power 5 and this specific equation, where he has shown that at long wavelength as well as at short wavelength, this distribution is actually following the energy distribution of a black body radiation. And that H is actually Planck constant, and the value you already know. And there is some, then Sir has discussed something about this atomic spectra that, and actually from Bohr's model, you are going to get these uh, I will say the, the equations to get the radius of an atom, or maybe momentum of an atom, or energy of an atom, right? And from there, actually, you are also getting one of the most accurately measured fundamental physical constant that is known as Rydberg constant. And this value is already given. And this this is an atomic spectra of a Balmer series, but this is not only related to the Balmer series, but there are other series of hydrogens, right? Kuhn series. Uh, I especially can't remember all the names, but Kuhn series, Brackett series, I guess, and these Balmer series, those are there. Those all follow these equation that 1 by lambda is equals to Rydberg constant multiplied by 1 by n1 square by 1 by n2 square. Okay, where n1 is, I guess, the n1 is greater than n2, or actually n1 is smaller than n2. So, so suppose your electron is hopping from n1 to n2, a higher state, then the wavelength it will radiate is this lambda. Okay, and then I'll go to the next. So, is there any doubt till now? You remember you have any specific doubt till this point of lecture? No, do you have any doubts? If not, I will go to the next lecture, the lecture two. Actually. So I'll just check if there is any message there. Uh, I don't think so. So I will go to the next lecture, lecture two. So it will again connect you. And as I told you that from the Bohr model of atom, you can see that angular momentum is quantized, and you can get the expression for energy or the radius. These all can be derived from the Bohr's model. But there are actually some limitation to Bohr model as well as, right? So there comes that Sommerfeld and all, who actually the limitations were will discuss. And as Bohr actually very specifically told that there are some stationary states where the electrons are allowed to rotate, no, rotate the nucleus, rotate around, revolve around the nucleus. But but it cannot actually uh, mm, say, or it cannot actually define that what is the reason behind the spectral fine nature. So that can be defined by actually Sommerfield model, where another subsidiary quantum number, azimuthal quantum number that has been introduced, that is mainly known as L in quantum mechanics, right? And your main stationary state is n, defined by n, and then that is your uh, primary quantum number, right? Principal quantum number, and then this is your subsidiary quantum number or azimuthal quantum number is l, and l is actually given by n to n minus 1, right? So for for n is equal to 4, you have uh, what here Sommerfield actually discuss it with a k. So for n equals to 4, it is k is equal to 4, n is equal to 4, it can be k is equal to 3. So there are actually 4, 3, 2, 1, actually four kind of uh, mm, orbits will be possible, elliptical orbits will be possible. And these are actually going to be your S, P, D, F, and all, right? And then Zeeman effect actually talk about the space quantization. This space quantization, like the about the restriction of the orientation of the angular momentum, right? That this is your angular momentum L, capital L, for n equals to 2, your L is given by root over n into n plus 1 each cut. So that is actually for 2, n equals to 2, it is root 6. 2 into 3 each cut, that is root 6. So that is the length of your here the orbital angular momentum, and each cut is actually acting as a unit chain. Okay? And your z component to that is actually mh cut. M is your magnetic quantum number here. Okay. For n equals to 2, as you can see, there are 5 m can be possible. That is m equals to 0, plus minus 1, and plus minus 2. Right. So in space, so actually from Zeeman effect, you are actually getting the how many uh, means you are getting an idea about the space quantization or the spatial position of this angular momentum. Okay. So from that, there actually comes the uncertainty principle, where I'm very sorry, my phone is ringing. And what does uncertainty principle tell? From Bohr's model, actually, as you saw, that it can give us the expression of the position, that is, and also as well as the energy, also the as it can give you, you know the velocity, you will be able to calculate from the position, you will be able to calculate the momentum, right? So from Bohr's model, what you are seeing, that it is actually you can specifically know your position and momentum at the same time, but that is not actually true. Uncertainty principle is a universal problem. That is, as Professor Datta has also told you, it is not limited to any instrumentational problem. That your instrument is not that uh, standard that you are getting this uncertainty. Actually, this is inherent to every system. So there will be some uncertainty to your position when you are measuring your position or momentum, and simultaneously you will be finding some uncertainty there, and that is given by this expression, that is delta x into delta px is greater than equals to h by 4 pi. So that is given by Heisenberg. So that is known as Heisenberg's uncertainty principle. So if you want to measure position accurately, you will, so that time your uncertainty in position will be 0, right? Then what will happen, that you won't be able to calculate your momentum. As you see from this expression, that if your uncertainty in position is 0, then your delta px have to be infinity. Then uncertainty in momentum have to be infinity to balance the equation, right? So, so if you want to calculate each of them accurately, that won't be possible. So there will be some uncertainty associated with that. With that, there comes Einstein's photoelectric effect, right? As you all know, and actually this actually talks about the wave particle duality, right? Einstein's photoelectric effect actually it tells you that these electrons are actually behaving like a particle, right? As it is hitting a metal surface, and if the energy is higher than that of your work function, then it will release some electron, and those electrons will have the kinetic energy P, and that is given by this equation that your whatever energy of photon, that is energy of incident photon is equal to your kinetic energy of your released electron and plus your work function, right? So from here, actually, we are going to solve some numerical problems tomorrow. So actually, if time permits, we'll do it today, and let's see what we can do about that. And then actually, the discussion actually goes to the wave particle duality. I will just finding the exact uh, position. So actually, there are different experiments have been done at different point of time, which actually is like diffraction of electron by Davison-Gardner's experiment. That actually tells you that electrons is actually creating a diffraction pattern, and diffraction creating a diffraction pattern means it is actually behaving like a wave. And again, what you saw earlier, that photoelectric effect of Einstein's model actually talks about the particle nature of the electron. So here actually the debate comes that are electrons wave or particle or both? It has actually from de Broglie's hypothesis, what he told that actually electrons can have both uh, this wave nature as well as the mm, particle nature, and he gave a expression of the wavelength of any matter is lambda is equal to h by p, that is actually h by mv. We will use this expression today explicitly to solve some numerical problem. So remember this expression that lambda is equal to h by p, that is given by de Broglie. So this is actually the wavelength of a matter. And suppose one electron, for a electron here, as you can see, the mass is 9.1 into 10 to the power. Yes, yes. Anyone? Any question? I have a message here. Oh, actually, I am presenting it from the laptop, and uh, uh, yes, Yogeshwaran, if you have any question, you can ask me. Hello. At this point, I can't hear you. You may write in the chat box. That I will. I can. And about this question, Nazira, I am actually presenting it from a laptop, so it is actually already full screen. I guess others are also can see my screen, right? Okay, then I'll go back to the teaching. Here I was. So what I was actually talking about the de Broglie wavelength, and here comes the interesting thing that uh, mm, Yogeshwaran, can you mute yourself, please? Actually, it is causing some noise. Can you please mute yourself? Okay. So we'll be going back to here. Yes. So what we are discussing actually de Broglie wavelength. Here I was talking about you. The interesting thing is all matter can have their wave-like property, and their wavelength is defined by lambda is equal to h by m. Now, suppose an electron which is moving by a velocity of 10 to the power 6 meter per second. And as you know, the mass of electron is 9.1 into 10 to the power minus 31 kg, very, very less. So as you can see, it will have a wavelength of 7 angstrom or so. And because of that, you can that electron can be diffracted because you're diffracted through some atomic slice of some metals because they have the atomic distance between them are in angstroms, so they can be diffracted. But what about a helium atom? So, and what I am trying to say, if a electron moving in this kind of speed, you will be able to see the wave nature of an electron. What about a helium atom? Which can, by some experiment, it has been shown that helium atoms at the speed of this velocity, as you can see, 2,347 meter per second, and when it is passed through a silicon nitride transmission gratings with 1,000 lines per millimeter, actually the de Broglie wavelength was calculated at 42.5 picometer, and the wavelength is very, very small here. As you can already think of, a 7 angstrom is already small, but to see some wave to diffract, your uh, grating should be as small as your wavelength or compatible so that they can diffract. What about a tennis ball or about a man who is moving like 10 meter per second or 1 kilometer per second? So that time you are going to see that a wavelength of a tennis ball or an elephant means a macroscopic element actually is very, very less, and it is so small that it can't be diffracted, and that's why we can't see the wave nature of a matter. We will be able to see something when it is getting diffracted, and there is no such uh, thing that can diffract that small wavelength of a macroscopic object, and that's why we don't really see them, see those, right? I hope there is no confusion till now. So I will just come to the now Schrodinger's philosophy, where what has been done, that as electron can be things of a wave and a particle, then all particles can have wave nature, and all waves can be things of the particle nature. So this was Schrodinger's philosophy, and Schrodinger actually gave a expression for matter wave, and that is known as the time dependent. I'll just see it here. Just using the already existing classical wave nature, he already give a equation for a matter wave, and that is actually your time dependent Schrodinger equation. I'll just write it from here so that it will be easy for you to follow. So I'll write it from here. Schrodinger time dependent Schrodinger equation. Okay, so that is given by IH cup, then capital psi, which is a function of x, y, z. This is your position and time. Del psi by del t, your time, and is actually given by a operator that is known as Hamiltonian, and obviously your wave function x, y, z, which is dependent on this. So here comes you first seeing this equation, which is a equation belongs to a operator algebra, right? So here H is actually Hamiltonian, and write it here. Age is actually Hamiltonian, Hamiltonian, also known as in classical mechanics total energy operator that will come soon, and given by your kinetic energy plus your potential energy. And your kinetic energy has a formula which participles by 2m del square. This is another operator as your potential energy. Okay. So your Hamiltonian can be broke down into this equation. I will not go down to this, but as you can see that your Hamiltonian is actually a function of your position, not space. Okay. Sorry, it's a function of space or position. It is not a function of time. And here is your, so what you can actually do is you can actually express this wave function as a product of two wave function, that is psi, that is dependent on x, y, z, t. Sorry, my bad. Psi, where it is a function of position and another is time. So this is very important. How you separate. So this is actually going to lead separations of variables. This is the first time you are seeing this, and you are going to use this technique in the end of this course. You are going to see what I'm trying to say in the future lectures, but this is very important. Where you uh, express your total wave function as a product of your spatial path and time dependent path. And so what might this equation become? It becomes I each cut del T of, I'll just write psi and phi. These are not capital psi, right? You know, and here it is psi and phi. As I told you that here we are discussing about del T, and phi is only here, which is a function of time. Psi is a function of space, so we can take this thing out. Psi into phi each cut del phi by del T. And here also phi is a function of time, not space. And Hamiltonian is a function of only work on the space dependent part. So this will act as a constant and it will come outside, and Hamiltonian will work only on the psi, the spatial. Here what I am going to do that I am dividing both the sides with capital psi, that is your psi phi. So it is going to become I each cos del by del phi del t divided by. So here what I have done, I'm doing a step jump. So I am dividing the whole thing by that is what we obtain. Okay. Now, as you can see that we have separated the variables. The left hand side, I will use another ink. So this part actually is a function of time. and this part has become function of space, right? So you have clearly separated these variables, and this can be equated only when they are equal to some constant. For now, let us see the constant is w. Okay, and from here you can write two things that you will be doing a step jump del phi by phi, and I will take w. I will take ih on this side and del t or dt this side. I can right now, as I have already separated the variables, now I can, instead of del, I can now use d. Okay? And for this side we'll have h I is equal to w psi, right? And this is where you are first introduced to a eigenvalue equation, where you can see when you have an operator operating on your wave function, that is lead to your wave function multiplied by some eigenvalue. What is this eigenvalue? This is actually your measurement. So you are measuring what is Hamiltonian. Hamiltonian, I told you, it is a total energy operator. So when total energy operator is operating on psi, it is giving you your psi with a eigenvalue that would be your total energy. That is your W is actually here energy. That is E. So one other way to write it is H psi is equal to E psi. And this is actually your time independent Schrodinger equation, which we are going to use more frequently to solve the different solvable systems. Now, what about this? We already know this W is E, and d phi by phi, when we integrate it, it will lead to, so if we integrate it, it will lead to you ln phi, ln phi. Uh, I can take this I to numerator by minus I. If you have any doubt here, please let me know. And I know my handwriting is not that good. If you have any doubt, please say me. I'll try to rewrite it. Your phi will be expressed as exponential of minus I w e by h. So your total wave function, the capital wave function psi, is phi obviously x y z function of this, and your phi you are getting as exponential minus I. Instead of w, we can write, obviously we can write e, right? Because we already know this w is e. Just here. Okay. So this is actually your total energy operator, which is your space dependent part, and the time dependent part you can able to solve it like this. Okay. So from here we can see we are introduced to two things, that this is a matter wave equation, right? And one more thing, that eigenvalue equation and operators, those are the things we are going to learn next, right? So I'll be again going back to the lecture. No? So that's all have been discussed here. As you can see what I have written there. I thought that if I write it down for you, then it will be best, instead of writing, just showing this equation. So there are some postulates now coming up, right? Some laws of quantum mechanics as this is written. So these postulates you can't prove them, but they are postulates. They are built on. Means suppose you can't really prove them, but they are the pillar of your quantum mechanics. Okay? You can now believe them as axiomatically. Now, what the first law of quantum mechanics or the first postulate would be that the for every classical variable there would be quantum mechanical operator. Okay. Like for position A, the quantum mechanical operator is A. For momentum, it is px, and px can be defined as a quantum mechanical operator like. And see these things, this hat is very important as a quantum mechanical operator. Don't so whenever there is a so you try to maintain this nomenclature of these conventions. I don't mean always try to write the hat. So it is a good practice. So what is Px? Px is defined by minus IH hat d by dx. Again, kinetic energy is also given by this kind of expression. We have already dealt with it just a little back, right? In total energy operator Hamiltonian, I showed you that it is a sum of kinetic energy and potential energy, where a potential energy in three dimension can be written like this. I took operator del square instead of this, right? And your potential energy is V of x. Okay. Now, what is the next law or postulate? You can say that for any observable, classical observable, you have a operator that we told you, and this operator is actually going to operate on your wave function and measure the exact value. So your wave function, that is psi n, has all the information. So by choosing an appropriate operator, you are asking questions. So you need to ask proper question to your wave function so that you can get your answer as your eigenvalue. So you can think of your operator as your question, which you are questioning your eigenfunction of the system that have all the answers. But that will give you answer when when you ask the correct question. I hope you are not uh, confused by the way I am speaking. I'm just trying to give you the gist of it. So your system has all the information. You just need to ask, use the right operator to get and write expression. And one more thing, these operators are all quantum mechanical operators are linear in nature. What do I mean by linear? Linear, and these operators are Hermitian as well. So I'll write it what I mean by linear operator. So all these, all quantum mechanical are linear operator. So by linear, what I am trying to say, suppose your C is your operator working on psi of n or psi. So your C can be, if your C is already, I'm sorry about this. If your C is already given something like that, this is the sum of A and B, both are operator. So your it is something like this, A and B, and will lead to A psi plus B psi. So your A and B are actually linear operators. So your all quantum mechanical operators are linear, and these operators, when they operate on your wave function, they will generate some eigenvalue along with your wave function, and this eigenvalue is always going to be real. Okay? Your psi can be complex. Okay. That you are going to see. That your wave function can be complex. But your eigenvalue value is going to be real for every operator, quantum mechanical operator. And that is a property of a Hermitian operator. I'll just, for now, I know you are not exposed to Hermitian, this kind of operator nomenclature. I'll just give you the mathematical description. For now, we'll discuss it later when I think Sir had some specific lecture where he taught all of this. But for the timing, I'm just giving you the mathematical description. I'm mathematical description. And that is, suppose you have a Hermitian operator A when it is operating on some wave function I, and there is another wave function like this, and you are taking an doing an integration all over this space, you are going to get phi star A, phi b tau, and complex conjugate of it. So this is the mathematical description of a Hermitian operator. That is, your A is Hermitian here. So if your A is Hermitian, then this is going to be the case. So for now, you don't have to be confused with this. This will come again. And for the time being, let us go back to the lecture. Okay, so for this, it is there, and now we are going to another lecture now, where now we will discuss that what is an wave function. Now we are discussing a lot about this wave function side, which has all the information, right? But how Max Born interpreted this, that we will try to understand. Till now, do you have any questions? Anyone? Uh, Navirab, means that is the maximum I can share actually. Okay, Vishan, go ahead. Okay. Okay, so if you don't have question, I will just go ahead. Okay, so the Born interpretation of this wave function is something like that. In a classical wave equation, you know your psi is given you amplitude, and your amplitude square is the intensity of your wave, right? Now, what does this tell us about our psi in a matter wave? So, in matter wave also, this psi square is an intensity, right? And we already discussed this our state or system will completely specified by this wave function psi of xt, which can be complex, which can be real. But let us, it is something like that complex number that a plus ib, b can be zero, but it can be complex. Okay. Now we already talked about it that we can get all the information, possible information can be derived from psi of xt, our wave function, if we ask it with the right operator. Right? Now what we are saying is that if this intensity is actually equivalent to probability, how can we say that? Suppose in this case, actually, Professor Datta has actually he given an example of a fly where whose legs we have printed with ink. So, if a fly with ink in his leg is sitting at a spot multiple times, that spot would be darker, right? So, the intensity of that spot is high. So, that means the probability of finding that fly is higher on that spot. So that is why it is saying that intensity is equivalent to probability. So if the intensity is high, then finding that uh, finding that uh, matter on that particular spot is high. Okay, so that's what mean by intensity is equivalent to probability. Next is your this psi xt mod square is actually not probability. Many a time in even in textbook also. So that is wrongfully mentioned that your psi square is actually your probability, but that is not true. This psi square, mod psi square is actually your probability density. Why I am saying so? You can see from the next bullet point. So your probability is actually the psi square into a volume element. So so when you so your probability is actually unitless, right? But your psi square, so your probability density when it is multiplied by the volume, then only you are going to get your probability, and that is your psi square t psi square multiplied by the volume element. And in three dimension, it is given by this xyzt mod square of that multiplied by beta. Okay. Okay. Now let us discuss. So I hope this is clear. Now the second thing is coming that suppose we are asking, so we are operating, we have the operator A, right? When we are going to operate in on psi, we are going to get some eigenvalue. But what is going to be the average value? So if we measure it multiple times, what is the so each time we can get different results. Okay. Now what is going to be the average value? And that is given by this notation average or expectation value of A, that is integration of psi star, that is the complex conjugate of psi multiplied by your operator A operating on psi. And there is a volume element. You can think of it as d tau, what we are discussing. And due to this bond interpretation, that this is actually psi squared t is actually a probability density, that actually leads to some extension, some extended postulates, or you can say extended rules, that your wave functions, not all wave functions are going to be acceptable quantum mechanically. So for quantum mechanically acceptable, your wave functions have to follow some basic criteria that I am going to write it here. So for acceptable wave function, first it will be square integral. I will write what do I mean by square integral. Okay. So square integrable means the your wave function have to be finite. So your at infinite plus or minus infinity, your wave function should have the value of zero. It can't have any means some value. It can have some value, but it cannot be infinite. So it will eventually have some normalization constant, and will be able to integrate it, and that's where it will be square integral. That is what mean by square integral. So your wave function have to be finite. That's what it all means. Then your wave function have to be continuous. It have to be a single value. There are many more criteria. One in such condition is also that your fast derivative of this wave function have to be continuous. But that is not that of a stringent criteria that can be actually avoided also. But that is another kind of criteria is there to be acceptable wave function. Now let's see that what are such some examples of wave function that are acceptable or not that we will see. So as you can see from here. So these wave function. So your x is the this is position on the x-axis and intensity of amplitude psi is on the y-axis. As you can see, when you go to the x is equal to infinity, your or x is infinity, then your psi is infinity. That is your this is not finite, right? So it is not an acceptable wave function. Again, another example, this is also an unacceptable wave function, right? Because at infinity, they might be zero, but they are not finite at x is equal to this value. So they won't be, we can't be able to integrate. So we won't be able to get the probability. We won't be able to get the value of the probability, and that's why they are not acceptable wave function. So actually, this acceptability is coming from the bond interpretations only. It is not coming from anything else. So, and there are some examples of acceptable wave function, as you can see here, that at infinity or at some points they are zero. So this can be integrable. So you can get the area under the curve, right? Here also. So, so this is looks like an exponential function. At infinity, it is going to be zero. Not at not it is not exactly zero at some value of x, but asymptomatically it is going to be zero at x is equal to infinity, and that's why it can be square integral. Also, this is another example. This is generally known as by a function sine x by x. I think that is also given in the week zero assignment, so that you can check. So this is actually an acceptable wave function. Why? See, first of all, this is continuous, right? Second, it is single value, right? Then what's the problem actually was with sine x by x. The orthodox view was that at x is equal to zero, it is sine x is also zero, x is also zero. So if so, the at x is equal to zero, the value is undefined, right? So but what exactly just before x and after x, the value are defined through limits and the value is 1. So it is a removable discontinuity. So you can think of it as a continuous function. And also, as you can see, the amplitudes of this damping motion is actually going to be 0 at infinity. So it will be the value of this function at plus minus infinity is going to be 0. So it is an acceptable wave function. Okay. Again, this is an unacceptable wave function because they are not continuous, right? Here it is an unacceptable because this slope at this point is different. So the d psi by dq is not continuous. Why this is why this is unacceptable? Because it is not single value. So your So one can have multiple value at x, but here we are dealing with the probability. Your probability can't be multi-value. Your probability has to be single value. The psi square del t, right? That is why this psi is not acceptable. Your psi has to be single value. And this is also it is not finite, so not square integral. So with those, these are the restriction we put on our wave function that psi must be an solution of Schrodinger equation. Psi must be normalizable, right? That means your psi have to be finite and zero at plus minus infinity or boundaries. Your psi have to be a continuous function of your variables, And in other way, another thing is there also d psi by dq or qed coordinate must be continuous. Psi have to be single value, and the point I told you that psi must be quadratically integrable. That means the square of the wave function should be integrable. So we can get the probability. So these are the restriction we put on the wave function, and with that, actually on the next week onwards, Professor Datta is going to talk about how to solve this exactly solvable system. So there are some exactly solvable systems like free particle, particle in a square well potential, hydrogen atom, rigid rotor. There are a few solvable systems are there, and where we will use the Schrodinger equation, and from the solution of this Schrodinger equation we will get the wave function of those uh, uh, system, and we'll see how the wave function or the energies are going to be quantized. Okay. Okay. So we are not discussing the free particle today. We'll I am just quickly go to the week zero assignment and some numerical problems. So let us first solve the numerical problems here, the week zero. So if you guys also can interact while solving this problem, then it will be very beneficial for you. So please try to interact. Okay. So the question was what is the frequency? So these are all based on the discussion we just had right now and what you have already known from the week one. Okay. So question one is what is the frequency of light having a wavelength of, so what is already energy is hc by lambda, also can be written as h nu. So what is the relationship between frequency and lambda? Mu is c by lambda. So here your lambda is known, that is 4.5 into 10 to the power minus 6 centimeter. So what is going to be your frequency, right? So you already know what is c. C is velocity of light or speed of light in vacuum, that is 3 into 10 to the power 8, or in other words 10 to the power 10 centimeter second inverse. And your I will not overwrite. I will just say that I should write. Your lambda is 4.5 into 10 to the power minus 6 centimeter. So I will just write it. And what do we have? We have 10 to the power 16 at the numerator and 1.5 at the denominator. Second inverse. So it is something like uh, I will again take this thing read 10 to the power 17 by 15 second inverse. I'll just use my calculator, or even without using the calculator. Let us see if we can get the answer. Huh? So, so this is actually 100. Let us say 100 into 10 to the power 15 second inverse divided by 50. Is this all right? So since I have broken down 10 to the power 17 as 10 square into 10 to the power 15, right? So this is something around 6 point something will be there. Something around 6.67 into 10 to the power 15 second inverse. So let us see what could be the answer. And we see that E is the correct answer. We don't always require the calculator, right? Sometimes we can do it right. Okay. Okay. I hope there is no question on this numerical problem, assignment problem. Go to the next one. So the question states that the Heisenberg principle states that. So what is Heisenberg uncertainty principle talks about? The first thing they have written is no two electron in the same atom can have the same set of four quantum numbers. So this is not true. So This is not true means this is given by Pauli, a Pauli's law, right? Pauli's what was that? Uh, this is given by Pauli. This is not by Heisenberg, right? So what does Heisenberg say? Heisenberg actually states this thing, third one. It is impossible to determine accurately both the position and momentum of electron simultaneously. That was given by delta uncertainty in position, right? Uncertainty in position, uncertainty in momentum is going to be greater than h by 4 pi. But sometimes we can also write it h cart. H cart is actually h by 2 pi. So you don't have to worry about it. Sometimes we write it for the sake of it. H cart by 4 pi. It also can be written as h cart. Means what I am trying to say. We can write it also h cart by 2 pi. 2. H cart by 2. Yeah. So that is what Heisenberg's uncertainty principle talks about. Okay. What about question number two? Oh, I have already marked it. So, which atomic orbital is spherical in shape? Obvious, yes. How does a 3p looks like? It is dumbbell shape, right? 3d and 4f are more complex, right? The s actually, the the s orbitals are all spherical. I think that's some message made something there. No. Then I will go back to the lecture. Okay. What about the question number four? That radiation of the radiation and matter both have particles and wave. What this property is called? First is given mixing, second wave particle duality, second quantum entanglement, third interference, four is written as confusion. So that is a very bad option. I hope you won't select this, right? So, so actually the answer is wave particle duality, right? So the radiation matter have both properties and that is known as wave particle duality. Now question number five, Max Planck's great discovery of was that the radiation of energy is emitted in packets. What does that packets called? Can any of you can answer this? Unmute yourself and can you give me the answer? What does this packet of energy is known as?
Quanta, sir.
Repeat. Can you repeat?
Sir, quanta.
Yes, it is known as quantum. Right. Quantum. A quanta of energy, and the energy is h nu, right? Okay. Now question number six. Uh, which of these following are acceptable wave function or not? So first of all, what are the uh, criteria of being an acceptable wave function? I told you that first it has to be continuous, right? Second, it has to be single value. Third, it should be square integrable, right? And some more. But let's see. I told you already this about this function sin x by x. Whenever this kind of question is given to you, try to plot the wave function. If you and this is these are just functions, right? Try to plot the function, and by plotting them, you will get the idea. So how does sin x by x looks like? Actually, sin x by x actually looks like this. Uh, we have the highest intensity here, and then again it will fall. Okay. So can we see the x? Okay. So as you can see, it is. And the fourth point is related to the square integral. It should be finite at boundary, right? So as you can see at plus minus infinity, it is going to be zero, right? So it is finite. It is single value. It is continuous. There is a discontinuity at s is equal to zero, but that is a removable discontinuity, and that you can do it by limit. And that's why this is an acceptable wave function. What about x sine x? You know how x, what is the plot of x? It is go diagonally, right? And what is sine x? Sine x is wavy. So actually sine x by x. So let me give you an example of an website where you can plot this wave function. You should try to do it by yourself first, but for the time purpose, I will just quickly show you how can you plot this. So there is a something called Desmos graphing calculator. So see, I will first do sin x by x. Huh? So this is how sin x looks like, and this is how sin x by x looks like. I'll just I'll just zoom out. Then you will see. Let's see. That is what we have drawn. So it has. That's how it looks like. Now let's see what x sin x looks like. Okay. So this is what x sin x looks like, and this is what your x sin x looks like. From here, you can easily say, obviously this is continuous. Obviously this is single value, right? But is it finite at your boundary condition? That is at your plus minus infinity. Is it zero? Is it zero? It's not. As you can see, it is going to be infinite at x is equal to plus minus infinity. So this is not an acceptable wave function. Okay. So your sin x by x, the x sin x is not a uh, acceptable wave function. What about sine inverse x? Let us plot it. What about sin x? What do you think? Uh, is sin x acceptable? Any one of you? What do you think?
So it is possible, sir.
It is possible. Why? Why? Why do you think? You are
So
correct.
it has a finite value.
Yes.
So it has a finite value, sir.
Yes. If you give it a finite range, it will be finite, obviously, and the maximum value it will have plus minus one, right? It won't go to infinite. So obviously there will be some normalization constant, but it is going to be finite. Yeah. Now we are discussing about sine inverse x. So let me see how does it look like. As you can see, sine inverse x at a particular boundary, it will looks like. So what do you think? Sine inverse x is means it is continuous. Obviously, at this boundary, it is square integrable. So this is actually going to be acceptable, right? So this is actually going to be acceptable. What about the last one? That is a e to the power. What do you think about a e to the power small a x square? Where a and this capital and small a are constant. So first let us think about how e to the power x square will look like. Okay. So if you actually plot it, it will actually give you a equation of how something like I'll show it to you. Looks like a parabola. Suppose I am writing e to the power x square. That is how it looks. What do you think? Is it acceptable? E to the power x square. Suppose as it was ax square, I will just write suppose 200, or instead of 200, let me write 0.2. A can be anything, right? So do you think e to the power ax square is uh, um, acceptable wave function or not? Any one of you? Can you answer? It's not finite, right? It's not finite at the boundary condition, or x is equal to plus minus infinity. It is going to be infinity. So this is not acceptable. But at the same time, if our this constant is negative, then it is going to be acceptable. As you can see, I am taking a suppose I am taking e to the power minus 2x square. Then you can see it is actually known as Gaussian function. So it has a maxima at x is equal to 0, and then from both end it is false off, and it becomes 0 at infinity. So this Gaussian kind of function, that e to the power minus ax square, if a is negative here, what I am trying to say, then your wave function is acceptable. So you have to write it like that. That if so, for this case, I don't know how will you choose the correct answer. But if you have a descriptive kind of question, then you can obviously write a when a is positive, it is not an acceptable wave function. When a is negative, it is an acceptable wave function. Okay. With that, we'll go to the next question, maybe. Okay, so actually we will not go to these questions because these topics are not taught yet. A particle in a box, or your hybridization, or conditions of a rigid rotor. So we are actually not going here. We'll solve eventually. These questions will come as a assignment problem in those weeks lecture. But I have gathered some, and as I told you at the beginning of the class, that I have gathered some numerical problems from Atkins physical chemistry books, and these questions we will we will try to discuss. These are very fairly easy questions, numerical problems. Not only this, I have a set of this. Obviously, I'm going to share this note or slide with you at the end of the lecture, but you can have the Atkins book and check the. So for here, I am using the 8th edition at the physical chemistry. So you can check the chapter number 8, where these numerical problems are there, and actually we are going to solve a few of them today. Right now the time is 8:30 or 8:25. We will try to solve as many as we can. Uh, as you can see, this question 8.1a and 1b are similar. 8.2a and 2b are similar kind of question. So I will solve one, and you try to solve the another one, and that will be your homework. So by that way, you will be able to solve. And these actually questions are based on the de Broglie wavelength and all that I told you, right? Okay. So let us see what the first question is asking. So it is asking that to what speed must an electron be accelerated to have a wavelength of 3 centimeter? So see, from de Broglie wavelength equation expression, what we know, your matter wavelength of a matter is going to be h by p, or sorry, uh, h by mv, right? M is mass, v is velocity, h is Planck constant. So here you can see that you already have the wavelength, that is 3 centimeter, right? You know what is Planck constant, right? And you know mass of an electron. So you will be able to calculate the velocity of the electron. So we'll do that. So the question is 8.1a. So lambda is given, that is 3 centimeter, right? Your mass of electron, 9.1 into 10 to the power minus 31 kilogram, right? You know the Planck constant, that is given as 6.626 into 10 to the power minus 34 joule second. Also, joule can be written as kg meter square second minus 2. How do I know that? Joule is energy, that is work done, right? What is work done? Force into displacement. What is the unit of force? That is Newton. Force into displacement, Newton meter. What is force? By Newton's second law, you know that it is mass into acceleration. What is unit of mass? That is kg. What is the unit of acceleration? That is meter second minus 2 multiplied by meter. So that's why I got kg meter square second minus 2. That is your joule, and it is joule second. So eventually it is 6.626 into 10 to the power minus 34 kg meter per second minus 1, because it is multiplied by second, right? So you need to know this kind of conversion for this solving this numerical problem. Okay. So from de Broglie expression we know your lambda is h by mv. So eventually your v is h by m lambda. So I'll just write 6.626 into 10 to the power minus 34 kg meter square second inverse divided by 9.1 into 10 to the power minus 31 kilograms, and lambda is 3 centimeter. 3 centimeter means 3 into 10 to the power minus 2 meter. So kg we can cut, meter gone. So what is the unit length? Meter second inverse. All are length. And what else is there? 6.626 and 10 to the power minus 34 in numerator and 10 to the power minus 31 minus 33 in the denominator. So eventually this is 10 to the power minus 1 in the numerator, and it is 9.1 into 3 in the denominator. So if you calculate this, I calculate using my phone's calculator. I will take some time here. It is 6.626 into zero point 0.1 divided by 9.1 divided by 3. And this is giving me something around 0.024 meter second inverse. So this is the speed of that electron, which will have a wavelength of 3 centimeters. So as you can see, the mass is very less and wavelength is 3 centimeters. 3 centimeters is a very big wavelength. That's why its velocity is very, very low. Okay. Okay. Now next question. So I hope you will. So I am solving the 8.1a, so you will be able to solve 8.1b, right? Because see, now instead of an electron, they have chosen a proton. So the proton wavelength is 3 centimeter. What should be the speed? So you need to know the mass of a proton. Okay. So just check the literature or from Google it. What is the mass of a proton? It is very, very less. It is actually I would say it's close to electron. It is very, very less than a neutron, obviously. It's something 1000 times less than that of a neutron. Just check it. What is that? Uh, I am not sure of the exact value. So I'll not telling you that, but just check it in the internet. What is the value? Now next question I'm going for is 8.28. The question says that the fine structure constant alpha plays a special role in the structure of matter, and its approximate value is given by 1 by 137. What is the wavelength of an electron traveling at a speed of alpha c, where c is the speed of light? Note that the circumference of the first Bohr orbit in the hydrogen atom is 331 picometer. When I first read the question, I was also afraid why this many terms are there, or what is fine structure constant. I did not know why these many terms are there. So I was confused. But see, actually, this is a very easy question. You have to neglect or you have to ignore a few things in the question. So don't think about what is alpha. Just see what the question wants. What is the wavelength of an electron? Same we go to de Broglie equation, lambda we need to calculate. The speed is given, the mass is known, that is the Planck constant. You don't have to understand what alpha is. The value of alpha is given, so we will not think about it. So let us solve this question. So now we don't know what wavelength is, but we obviously know what mass is. 9.1 into 10 to the power minus 31 kg, right? What velocity is mv? That is same alpha c. Value of alpha is given by 1 by 137. The c is, you know, c into 10 to the power 8 meter second inverse, right? That is given. What else is given? Planck constant. That is, you know, that is not given. These are the some constant you can always remember, right? 34. I'll again write kg meter square second minus 1. Okay, just check the previous slide. Why I'm just done a step chart. So actually your lambda is going to be h by mv, right? 6.626 into 10 to the power minus 34 kg meter square second minus divided by m is 9.1 into 10 to the power minus 31 kg into the velocity is 1 by 137 into 3 into 10 to the power 8 meter second inverse. I'll cut the units. Second inverse one meter, meter 1 kg, kg gone. Okay, so my unit left is meter, and I will see what else is remain. 6.626. What about 10 to the? It is 10 to the power minus 3, 10 to the power minus 11 divided by 9.1 into, and also 137 I took it to numerator, and 3 is there. So I'll just calculate again using my phone's calculator. That's 6.626 into 137 divided by 9.1 divided by 3. So into 10 to the power minus 11. So that is actually giving me a value of 3.325 into 10 to the power minus 10 meter. That is actually angstrom. 3.325 angstrom. You should know that the relationship between each units. Okay, we'll eventually solve those questions, but you have to know this thing eventually. Okay, I hope You got the idea how we are solving this? We are only using the de Broglie equation expression for this question. Nothing else is required yet. Right? So, what does question number 8.2b says? Calculate the linear momentum of photons of wavelength 350 nanometer. What speed does a hydrogen molecule need to travel to have the same linear momentum? So, suppose your lambda is given, then photon is there any question particular? I'll just check once. And then okay. 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 So let's go back here. So calculate the linear momentum of photons of wavelength 350 nanometer. What does a hydrogen molecule needs to travel the same momentum? So wavelength is given. You know the Planck constant again. So you will get the momentum P, right? Now your hydrogen molecule, so now your hydrogen molecule needs to have the same momentum. So just replace the momentum value of hydrogen by whatever you are getting here, right? So what would be the speed of hydrogen? So, so let me at least write it. So, so first of all, your lambda is given 350 nanometers. So, so that photon have momentum. Sorry, what is this? P is equal to 6.626 into 10 to the power minus 34 kg meters per second per divided by 350 into 10 to the power minus 9 meter. Okay, I'm not solving it here. Now it is said that your hydrogen molecule also have to have some speed to have this linear momentum. So what is the mass of hydrogen? So that is 1.008 atomic unit, and you need to convert it to kilogram. That you can do it by multiplying this with 1.66 into 10 to the power minus 30 minus 27 kilogram. Okay, so this is mass of one hydrogen. So now you have your momentum, you have mass. So to have the velocity, so velocity will be momentum 6.626 into 10 to the power minus 34 kg meter square second inverse divided by 350 into 10 to the power minus 9 meter divided by this 1.008 into 1.66 into 10 to the power minus 27 kg. So kg gone, meter gone. So velocity. You are left with the unit meter second inverse, right? And I will just calculate it using my calculator 6.626. I hope you are getting what I am discussing, right? Can any one of you respond if you have any doubt in these questions till now? Please respond. Any doubt so far? Anyone? So I'll just write the answer and then I'll check the comment section. I think someone has written something. And this is coming as 1 point. Um, I'll just again one. response calculated 6.626 into 10 to the power minus 34 divided by 315 divided by 10 to the power minus 9 divided by 1.008 divided by 1.66 divided by 10 to the power minus 7. So that is 1.1313 something. So 1.13 meter per second. I hope this is the correct answer. You also try to check the answer. Huh? Oh, that's all. Great. Uh, okay. So let us get back to another question maybe. So 8.2b we have solved. Now let us see what is there in 8.3a. The speed of certain proton is given, that is megameters. Oh my god. That is a unique unit, right? Which don't really see this unit often here. So mega means 10 to the power 9, I guess. 10 to the power 9 meter. Nanometer is 10 to the power minus 9. Mega is 10 to the power, what I'm saying. Mega is 10 to the power 6, right? Mega is 10 to the power 6. Am I speaking sense? I will just check once in internet. Yes, megameter obviously is 10 to the power 6. A gigameter is a gigameter is 10 to the power 9. Just for your information. So the speed of proton is given 0.45 megameters second inverse. If the uncertainty in its momentum is to be reduced to 0.01%, what uncertainty in its location must be tolerated? So obviously from the question you got the idea that this is related to Heisenberg's uncertainty principle, right? So we'll first write that. Oh, I don't have any more slides. So just copy paste some of them. Okay. 8.3a. Heisenberg uncertainty principle, we know delta x into delta px, uncertainty in position and uncertainty in momentum is greater than equals to h cut by 2. So the minimum uncertainty, if we think of like that, it is delta px is equal to h cut by 2. Okay. Now what does the question want? Question says that uh, uncertainty in its momentum is to be reduced to 0.01%. Okay. So that is 0.01 into 0.01. So what uncertainty in location must be tolerated. So this is given as 0.01%. That is actually, to be honest, 10 to the power minus 4, right? So your delta x is going to be h cut by 2 into 10 to the power 4, or better like this. So this is so 6.626 into 10 to the power minus 34 joule second into um, 10 to the power 4 divided by 4 pi, that is 4 into 3.14. What will be that value? And just calculate 6.626 into 10 to the power minus 34 into 10 to the power 4 divided by 4 divided by 3.1. Something around 5.28 into 10 to the power minus 31. See, the uncertainty in location is very, very less, right? Compared to that. So this is the uncertainty in location is going to be, or the tolerance range. When the uncertainty in your momentum is 0.01%, then your uh, uncertainty position is going to be like this. Okay. Now let us go to the next question. Similar question is there in 8.3b. I am not going there. 8.4a. Calculate the energy per photon and energy per mole of photon for the radiation of wavelength 600 nanometer, 550 nanometer, 400 nanometer. So what is the energy of a photon? You know, energy of a photon is given by hc by lambda of one photon, right? Now, if you replace lambda by this value 600, 550, 400, you are going to get energy of one photon of this wavelength. And what is the energy of per mole? So per mole you need to multiply it by Avogadro number and your unit. So unit of energy for one photon, it is going to be in joules, right? So you will check that 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 meter the second inverse pi lambda. By that, somehow it is going to be joules, and your suppose the energy per mole is going to be joule per mole inverse, and that is actually coming from your multiplied by Avogadro number. The Avogadro number is given by 6.023 into 10 to the power 23 mole inverse. So in one mole, there is going to be this many number of photons are going to be. So that's why if one photon, energy of a photon is hc by lambda, then energy of your Avogadro number of uh, photons are going to be a Avogadro number multiplied by your hc by lambda. I hope this is you are getting it. I am not solving it explicitly, but you can try it for 8.4a and 8.4b. Right? Okay. Now let us check the next question, which is 8.5a. Calculate the speed to which a stationary hydrogen atom would be accelerated if it absorbs photons using the exercise 8.4a. These wavelengths you need to consider lambda is equal to 600 or 550 or 400. So it is saying that calculate speed to which these stationary hydrogen atoms would be accelerated if it absorbs each of these photons. Hello. Oh, thank you very much. But you should try to check the try draw the plot by yourself first, and then Desmos is or the graphing softwares are always there. So uh, that's a good way to check the wavelength, a wave function, right? Anyway, so okay, let us come back to this. Calculate the speed to which a stationary hydrogen atom would be accelerated if it absorbs each of photons used in this. So obviously, you what expression we can use it here? We can use so to understand how many. So if it absorbs one photon of 600 nanometer, then it is absorbing energy of hc by lambda, right? So that is the energy, and energy is related to the momentum by p square by 2m. Okay, you know mass of hydrogen right now. You know the energy. Mass of hydrogen I already told you 1.008 into 1.66 into 10 to the power minus 27 kilograms. You need to convert from atomic unit to the kilograms, right? From here you will going to get the momentum, right? And again you have m at your hand, so you are going to get the speed here, right? Actually, you can write it something like half mv square. Half mv square is going to come, right? M square, v square, 2m, so half mv square. You know the m, you know energy, so you from there you can calculate the speed, right? Actually, I'm not solving it explicitly so that you can try both the question, and that would be a good practice, right? I'm just giving you the expression, so it won't be a that hard to solve, right? Anyway, these are very easy problems. These are actually very fundamental questions that you should be able to solve before going into the uh, mathematics part of the quantum mechanics, like the solvable, exactly solvable systems and all. So let us solve maybe this 8.6a and 8.7a, and that then we will stop for today, right? Because it will be almost around 2 hours, and the materials is enough for 1 week, I guess. So, and I will share these questions with you. So you try to solve this question this from 8.88 these onwards, the second and third slide, so that we can discuss it on the next day. So you will be able to be more interactive, right? So I'll expect that you are going to solve these questions at home, and uh, when I am trying to solve it here, I will ask any one of you to solve it on my behalf, or I will need your help. Whenever I will need your help, I will ask twice. Okay? It's not like that I am going to solve it correctly every time. You need to correct me if I am doing anywhere wrong. Okay? Anyway, so now let us solve this 8.6a. The question says a glow worm of mass 5 grams emit red light, that is 650 nanometer, with a power of zero point 0.1 watt entirely in the backward direction. To what speed will it have accelerated after 10 years if released into free space and assumed to live? So that is a very confusing question, and lot of information is given. So we need to digest it. First of all, don't think what system they are saying. So it is said that a mass of 5 gram is there, which is emitting red light with a power zero point 0.1 watt. What does zero point 0.1 watt means? It means per second it is releasing zero point 0.1 joule. Okay. The question is asked that what will be the speed of this mass after 10 years? Okay. Wait. So now we will try to solve it. 8.6. Mass given is 5 gram. That is 5 into 10 to the power minus 3 K. Okay. So it is radiating a light of 650 nanometer. Okay. And it is released for 10 years. So What is the time? 10 into 365 days into 24 hours into 3600 seconds. So how much time is that in seconds? Let me calculate. 10 into 365 into 24 into 3600. So that is somewhere around 315,360,000 seconds. Now, the power is also given is 0.1 watt, that is 0.1 joule per second, joule second inverse. So you can understand how much power it is going to release for 10 years. The total power, actually multi P into T, right? Not capital is not small p, it is capital P. So that is going to be your 0.1 into that. So that is actually 3.1315360000 joules. Okay, this many joules it is going to radiate. Now, actually, you will see the question says it is radiating backward. So actually, this actually gives its momentum. Okay, we have to understand how many photons did it release. Before that, we need to understand what is the energy of each photon. So, energy of each photon, sorry about that, is hc by lambda, right? So lambda is, so I'm not writing it explicitly, it is 650 nanometer, right? So this mostly it will come in joules. So so with this power, how many photon is there? So total number of photon is going to be this 315,360,000 joules divided by AC. I will now write 6.623 into 10 to the minus 34 joule second into 3 into 10 to the power 8 meter second inverse, and 650 nanometer will come at the numerator. So I make it in meter, nanometer to meter, so that I can cut this unit, right? Joule, joule cut, second, second inverse cut. So this is what is left. 315,360,000 into 650 into 10 to the power minus 9 divided by 6.626 into 10 to the power minus 34 into 3 into 10 to the power minus 8. 3 into 10 to the power 8, not minus 8. Right? So this is the total number of photons. Now, let us go back to the question. So this is the total number of photons that is radiated by this mass. Okay. Now, what is going to be the, so when it radiates one photon, then it is gaining some. So as you know from the Newton's third law, it is radiating something. So actually that is as a reaction, it is going, uh, as it is free space, there is no friction. So it is going forward. So after releasing each photon, it is gaining some velocity. So that is again from de Broglie wavelength. You are going to get the momentum. Mass is given. So for each photon, momentum gain is p is equal to h by lambda, right? So lambda is also known 650. I'm not writing it here. So the total momentum gain after releasing so many photons, this is this 3153600 into 650 into the minus 9 divided by 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8. This many number of photons into h by lambda again, right? So this is the total momentum. You know the mass, so you can calculate the velocity. So velocity is total momentum by mass. So I have to write it again. This is 000 into 650 nanometer. I'll write it again. Oh, I should not write it nanometer. Then I have to wait. I'll just do what I was doing. 650 into 10 to the power minus 9. 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8. H is 6.626 into 10 to the power minus 34 joule second. Lambda is 650 into 10 to the power minus 9 nanometer. So these are gone, but the unit remains, right? And divided by mass, mass is 5 into 10 to the power minus 3 kg. Joule is there, joule second. What is that? I told you kg meter square, second inverse. Kg gone. And 615 10 to the power 9 minus 9 not nanometer, it is in meters. So 1 meter will gone. So the unit left is meter second inverse, right? So we have to calculate this. What we have to calculate, I will just quickly write it here. 31536 divided by 3 into 10 to the power 8 into 5 into 10 to the power minus 3. This is going to be your answer. And what is the answer? I will just give you. I hope you are getting what I am trying to do here. This is actually a bit confusing, but if you see that once again, you will be able to get the answer. So it is coming something around 21 meters, 1.024 meters second. So this is the velocity that it has. So I hope actually this question was a big question. So if you try to solve 8.6b, the same question, but just numerical, the numbers are different. So I hope you will be able to solve that. I'm not going to talk about 8.7a today because it is already time. It is already 9 a.m., 9 p.m. Sorry. So many of you have to take your dinner. Me too. So let us call it a day. I hope you will try to solve these questions. And this session was uh, informative to you. I hope you got some help in get some help in solving the assignment one numeric. And please try to solve the assignment problems as well as these numerical problems what I'll be giving you in the notes. Or from you can also look at the actions directly. It will be helpful. So with that, today uh, stopping. So
Thank you, sir.
yeah, no need to call me sir. Just you can call me Bhaiya or you can all anyway you can call me directly Orko also. So no sir.
Okay, thank you.
Sir. Yes. Okay. Good night. We'll meet you on the next session. Thank you for joining.
Good night, sir.
Good night.
I mean,
So I'm stopping the session, guys, and speaking.
okay, sir. Okay,
Yeah. No sir. I get it.
okay, bhaiya.
Yeah. Okay. Meet you sir.